Hi folks, today we're going to be looking at some problems that use the laws of logarithms. So let's get started. Expand log base 7 of 49 times x divided by y. There's a few ways to approach this, but I think the most obvious is looking at that quotient. We can use the quotient rule for logarithms, which states if you have a log base b of x divided by y, you can just write that as the log base b of x minus the log base b of y. Now we have a 49 in here, so that'll make things slightly different. Instead of x, we have a 49x in the numerator. So this begins with log base 7 of 49x minus log base 7 of y, since 7 is in place of our b in our quotient rule. Now if we wanted to expand it a bit more, you can look at, you have the log base 7 of 49x. That's a product of two terms, and the two terms are 49 and x. So an easier way for us to write that, we can use that product rule for logarithms, which states the log base b of x times y equals the log base b of x plus the log base b of y. So you get log base 7 of 49 plus the log base 7 of x, and then we still have that minus log base 7 of y. And the log base 7 of 49, that's just the log base 7 of 7 squared, and then we have the rest of our terms sitting right there. And the log base 7 of 7 squared, if we wanted to make that simplified, it would be 2 plus log base 7 of x minus log base 7 of y. Notice though, at actually the second step, we were done. We've expanded it. It's just a little bit of simplifying that we've done here. Any of these last three answers will suffice. So just keep that in mind as we move on. Evaluate the log base 6 of 56 plus the log base 6 of 54 minus the log base 6 of 14. So when we take a look at this, we're going to use our laws of logarithms once again, and we'll begin this one by using the product rule. So with the product rule, that means when we have the sum of two logarithms, we can combine them into one. So if we have the log base b of x plus the log base b of y, that's the log base b of x times y. So taking a look at that, we can rewrite our first piece as the log base 6 of 56 times 54, and then minus that log base 6 of 14. Now with that minus sign sitting there at the end, we can now use the quotient rule for logarithms, which states we have the log base b of x minus the log base b of y. That should be the log base b of x divided by y. So taking a look at this, this now becomes log base 6 of 56 times 54, all divided by 14. And we can do a little bit of simplifying, just plug that in, and we see that that inside number is 216, and 216 is just 6 cubed. So we have the log base 6 of 6 cubed, and we know since this log base 6 and then that 6 raised to the exponent, those two functions there are inverses of each other, so our final answer is just 3, just by our properties of logarithms there. Hopefully this allows us to see how these logarithms can work. When we can't even evaluate with a calculator, it seems at first, we can do some of these in our head just by using these laws of logarithms, and that's the power of them. Moving forward, let's take a look at problem 3. Rewrite the log base 5 of x plus 3 minus 4 times the log base 5 of 2x minus 7 plus 1/2 times the log base 5 of 4x plus 1 as a single logarithm. So we want to do some combining, but notice immediately we have some numbers out in front of each of these logarithms, even though they all are the same base. So in order to handle that, we need to start with the power rule for logarithms. And that power rule says if you have r times the log base b of x, that is the same thing as the log base b of x raised to the rth power. So we can rewrite that minus 4 log base 5 of 2x minus 7 as 2x minus 7 raised to the 4th with a log base 5 surrounding all that. And for the 1/2 log base 5 of 4x plus 1, we can rewrite that as log base 5 of 4x plus 1, that quantity raised to the 1/2 power. So that's just using our power rule for logarithms there. Now, if you take a look, we can combine the first two terms. You have a minus symbol there, so we use the quotient rule for logarithms, which is the log base b of x minus the log base b of y should be the log base b of x divided by y. And what actually happens in this case, we have in our scenario, it's just combining that x plus 3 and that 2x minus 7 raised to the fourth power into that single logarithm. So you have log base 5 of x plus 3 over 2x minus 7, that quantity raised to the fourth, plus the log base 5. And if you notice, we have 4x plus 1 to the 1/2. Well, the 1/2 power is just a square root. So log base 5 of the square root of 4x plus 1. And that plus symbol, now we can use the product rule for logarithms, which states if you have the log base b of x plus the log base b of y, that should be the log base b of x times y. And so multiplying those on out, you get the square root of 4x plus 1 multiplied by that x plus 3, 2x minus 7, that quantity raised to the fourth. This leaves us, if you want to make it look a little bit nicer, you can move that square root of 4x plus 1 into the numerator, since multiplication is the same thing as square root of 4x plus 1 over 1, and multiplication on fractions goes straight across. And so our final answer is log base 5 of x plus 3 times the square root of 4x plus 1 all over 2x minus 7 raised to the fourth power. Notice we only have a single logarithm with a log base 5 here. Okay, approximate the log base 7 of e to the fifth to 5 decimal places. So in this case, we're going to need to use the change of base formula. And the change of base formula says if you have the log base a of x, that's the same thing as the log base b of x divided by the log base b of a. In our case, the base that we want for b is either going to be 10 or e, due to the fact of those are our main buttons on our calculator, because log base 10 is just log, and the log base e is the natural log, denoted by ln on our calculator. So taking a look at this problem, when you have the log base 7 of e to the fifth, let's use the natural log, because you have that e to the fifth sitting inside of there. It'll make it a little bit nicer for us. So we begin by using our change of base formula, log base 7 of e to the fifth. That should be the same thing as the natural log of e to the fifth divided by the natural log of 7. And the natural log of e to the fifth, that's a pretty easy calculation, because natural log and then that e, they're inverses of one another, essentially. So you have, this just becomes 5 in the numerator, so you have 5 divided by natural log of 7. And now we can just punch that into the calculator. So pull out our calculator, and with our calculator, the first button we want to push is the 5, and then we hit divided by, and you can see the natural log symbol appearing over here on the left hand side. So we hit natural log, then we punch in 7, close off our parentheses, and then just hit enter, and we get our final answer. So this is an approximation since we're rounding 5 decimal places, so we get 2.56949. So we can take this idea, this change of base, and we can apply it to many different types of problems, and we'll take a look at another one in this next problem. So rewrite the log base 3 of 1111 as an equivalent ratio of logarithms with base 10. So base 10, if you recall, is a common logarithm, so this should just be log. Okay, and so with that in mind, we can rewrite this using our change of base formula. And so once again, as we mentioned before, our change of base formula is given by log base a of x equals log base b of x divided by the log base b of a. And so in our case, what are we going to want? Well, we're going to want our a value to be 3, our x value to be 1111, and since we want to convert it to base 10, our b value is going to be 10, which we can just denote by log now. And so this becomes the log base 3 of 1111 is equal to the log of 1111 divided by the log of 3.